Welcome back to the next concept on standard normal distribution. So by this point, you should already understand what normal distribution is and how it applies to continuous random variables. So this is a brand new concept that at first may feel a little bit abstract. And when I was in your shoes, first learning this concept from my tutorial notes, I couldn't really understand this concept and I memorized it the way as it is. But that's definitely not the way to do it. So I'm going to explain to you how this works using a very simple example. And then once I explain how it works already, then I will show you how we actually use it in the context of exams. Okay, so let's first talk about a very classic example. Okay, so let's say I have two continuous random variables. Okay, so I say let x be the random variable. Okay, so this is one continuous random variable, and let me just zoom in, that represents math scores in a class. Okay, and then we repeat the same thing. Y be the random variable that represents, let's say, English scores in a class. Okay, so let's say, X and Y, there are two different random variables. And then let's say, for example, X follows a normal distribution of, let's say, 60 and let's say 10, right? So just a recap, what this means is that this 60 is the mean and then this is the variance, right? Standard deviation squared. Now let's say I have Y also, and Y follows a normal distribution of, let's say, 70 versus 5. Okay, or maybe I make the example a little bit more extreme. I put the mean away. Okay, so 80. So if I were to draw out these two graphs over here, right, using the probability density function, you see that X mean is 60. So let's say 60 is here. And 10, the variance is larger than this. So having a larger variance essentially means the data is more spread out. So if let's say this graph over here looks like that, okay, we will expect this graph over here, where here's 80, to be a lot skinnier, right? It's a lot skinnier because this variance is lesser, and we know that the standard deviation is root 5, right? This is the standard deviation, whereas the standard deviation for this is root 10, and root 5 is smaller than root 10, right? So since the standard deviation is smaller, we will expect, the standard deviation, smaller standard deviation, to have a skinnier curve in that sense. So now that we painted this example over here already, then let me pose a question. Okay, so let's say I say that person A scored, let's say, 70 for math, okay, and let's say person A scored, for instance, let's say person A scored 85 for English. So if person A scored 70 for math, maybe person A is somewhere here, right? This is 70. And then let's say, oops, I'm just going to label here as 70, yeah? So here's 70. And then let's say 85 is here. Oops, not really here, but here. Okay, and then let's say 85 is here. Then what if I ask you this question, right? Then from here, I ask you, which test did person A perform better in, right? You see that if we just compare side by side like this, it's very hard for us to tell whether person A did better for math or better for English, right? And that's simply because these two curves have different spreads. This mean over here is 60, whereas this mean over here is 80, right? This standard deviation here is root 10, whereas this standard deviation here is root 5. So it's very hard for us to compare raw scores like that. And in order for us to compare these two scores, it is indeed possible, right? In order for us to compare these two scores, we need to have a common point of comparison. We need to have a standard, or rather same distribution, whereby these two values can coexist at the same time to actually compare these two values, right? In simple words, we need to have a common platform of comparison. So by observing, we can't really compare, but what we can do is that we can standardize these two different graphs. Okay, so I'm just going to write here. From here, we see a problem, right? The problem is that we cannot directly compare as the two graphs have different scales. So if the two graphs have different scales, then how do we work around it? The solution is we transform both graphs into the same scale. And I'm going to show you how we actually transform these two graphs into the same scale. Okay, but this is so far the context of why we even need to, learn this concept in the first place. Okay, so I'm just going to bring this down here. So how do we actually transform this two? For each graph over here, first thing is, or rather it's 2 steps. The first step is that I'm going to shift both graphs mean value to 0, which means I will make the mean value to be 0. And how I do this is that I shift this graph to the left by 60, and I shift this graph to the left by 80 first. So essentially what I'm doing is x minus 60. So every single x value, right, I shift it to the left by 60. So now my mean value hovers above 0, and the variance is still 10 in this case, okay? And then for the one on the right, I shift to the left by 80 units. So now every single value minus 80, and now the normal distribution, the mean value is hovering above 0, and the variance is still 5, okay? So if I were to draw it out, this is how it will look like now. So let's say here is 0. Now the whole graph, yeah, I'm just going to copy this, and then I'm going to paste it here, right? So now this hovering right above the 0 value here. Same thing for here. Let's say I copy and I paste, right? I shift it to here, and then now here is 0. So that means now this value over here, the initial value of 70, is now 10, right? And then now this initial value of 85 over here is now, so we are getting closer to the same scale, because at least now these two are hovering above the same mean, so to speak. But then the challenge is we still cannot compare these two because the variance is different, right? The variance for this is 10, therefore it's a little bit fatter and shorter, whereas the variance for this is 5, therefore it's a little bit skinnier and taller overall. So we need to resize these two graphs to be the same shape first. We need to resize these two so that the height and the width of these two graphs are now the same. So how do we do that? Currently, this gap over here, right, this width, you can think of this width as root 10. And currently this width over here, you can think of it as root 5. Now, a very easy way to make these two widths the same is to take the width and divide it by itself. So divide, or rather make the width of both graphs the same by dividing all the values by the standard deviation. So, okay, I'm just going to take this whole thing here and shrink it, and I'll just chuck it at the corner here. So what this means is now for every single x value here, I am going to divide it away by root 10. And when I divide it away by root 10, this gap over here, root 10, divided by root 10, right? You see root 10 divided by root 10 gives me 1. So now the variance is 1, which also means the standard deviation is 1, right? And then for this 80, for this graph over here, I will divide it by its standard deviation so that the variance is also 1. So you can see that now we have done these two steps. These two graphs over here, they have the same parameters already. Both graphs now have the same mean and same variance standard deviation, which means that this graph over here now hovers above 0. Okay, I'm just going to draw the 0 here, up, down, and the standard deviation here has a value of 1, right? Because my variance is also 1. So by standardizing both this way, we can then compare who or which test perform better. Because all we need to do is to take the original score. So let's say 70 for math, right? So let's say for the math score, right? 70 minus 60 divided by root 10. So we get the position of this score on the graph. And that will be 3.1622 ... Right? So that means my math score is somewhere here, 3.16. And then my English score would be to follow this equation over here, because it originally was on this graph over here. So 85, right? So I just need to sub 85 over here. So that means I take 85 minus 80 over root 5. So 85 minus 80 divided by root 5. I get a value of 2.2360 ... That means my English is somewhere here, right? 2.24. So it is clear for us to see that he performed better in math because the percentage of people who actually got his score in math is lower than the people who got his score in English, right? So what you have seen is this thing called standardization. So what we have done is that we have effectively taken these two graphs of different parameters, and we have standardized both of them into the same graph. I'm just going to draw it nicely here, right? What we have just done is this thing called standardization. standardization, whereby we standardize the mean to be 0 and the standard deviation and the variance to be 1, right? And this graph over here, this standardized graph, has a symbol that we will always use. And this symbol is the letter Z. So whenever you see this symbol Z, right? Whenever you see Z follows a normal distribution of this, sometimes we call this the Z curve. And the Z curve is essentially a normal distributed curve with specifically 0 as the mean and 1 as the standard deviation of the variance, right? So this is the whole idea behind it, why we actually do standardization and the concept behind standard normal distribution. So I don't want you to just learn it and just memorize it and take it as it is, right? At least now you understand why we learn it and why we actually use it. Because in exam situations, when you read questions and then you realize that I need a tool that allows me to do a comparison between two different distributions, you will recall of this example and use standard normal distribution to help you solve the question. Okay, so this is the whole idea behind it. So with that said, now down to this question over here. We're going to attempt these questions over here. I'm going to show you examples. Use this page over here to show you an example of how to actually tackle these questions using your GC. And in fact, it's very simple. It's the same as your previous normal distribution questions. It's just that now specifically, we know that the mean is 0 and the standard deviation is 1. Okay, so if you're feeling confident, feel free to pause this video right now, tackle this question. If not, you can just follow through with the solution that I'm about to show you right now. Okay, if not, let's start to tackle this question right now. All right, so let's start with question 1. And before we even start question 1, I will draw out the graph to actually try to visualize what we are trying to do. So we know that Z is a special alphabet reserved for the standard normal distribution. And the standard normal distribution curve has the parameters of 0 as the mean and standard deviation and variance as 1. So if we were to sketch out the graph, let's say here is the values, right? This is the Z value. And then from here to here, we know that here is 0, right? And we're trying to find the probability of a Z value falling between -1 and 2. So effectively, we're just trying to find out what is the area underneath this graph. And that is represented by part I, which is essentially the probability, right? Because the probability is the area under the graph between 1 and 2. So once again, recap that your calculator, actually not, yeah, your calculator is able to calculate this directly. And what you want to do is you want to come back to your GC, second DISTR. So at the core of it, a standard normal distribution is still a normal distribution curve. So you can still use normal CDF for this. You click enter. So your lower limit is now -1, upper limit is 2, and then just nice, these two values are already there. Right, just paste, enter, 0.81859. So I'm just going to come back here, 0.81859 ... which is 0.81923 SF. That means this area is 0.819 units out of the whole entire area of 1. Okay, so now let's move on to double I, and we want to find out what is the area below -2. So what we can do is second DISTR here. Lower limit is -1E99. So just as a tip for you, -1E99 means negative infinity. So that means you are, all the way lah, because it's below -2. So anything below -2. So we effectively start from negative infinity onwards. Upper is -2, and here that's the rest is the same. Enter. -0.02275 ... right? And then just 3SF it, 8 to 3SF. So that means what we're trying to do is, let's say I extend this graph a bit more, right? Extend it, then let's say this graph extends a bit more. Over here, let's say this is -2, right? We're just trying to find out what's this area here. And this area over here would be this, okay? Now, triple I would be P, Z is bigger than 2. So P, probability of Z is bigger than 2, on the graph would be this area, right? Bigger than 2. So this is the whole area that we're trying to find. But again, remember our calculator cannot calculate things that are above, only can calculate things that are below. So what we can do is we can find the complement of it, which is 1 minus P, Z lesser than 2. So we effectively take the whole thing, then we minus away everything below here, and then we are able to find this, right, which is the complement. So in the calculator, all we need to do is to just key 1 minus the normal CDF. Upper will be 2, and then all the way down here, right, paste 0.02275. Yeah, effectively it's the same thing. Yeah, correct. It's the same thing. So you get 0.022750 ... which is 0.0228223 SF. And the reason why these two values are the same is because if 0 is the center line, so imagine 0 here is the center line, right? The distance from 0 to -2 and the distance from 0 to 2 is the same, right? So since these two distances are the same, that means this whole area here effectively is the same whole area over here, right? Because the graph is symmetrical about this line over here. That's why both answers are the same. Okay. Lastly, we have P modulus Z is bigger than 1. So this one goes back to your what you learned in inequalities. So if you have modulus Z is bigger than 1, that means you have Z value bigger than 1 or Z value lesser than -1, right? That is the two inequalities that you need to add. So effectively, we're just trying to find out these two added together, what's the value. And recall that for this, we cannot directly find it because it's bigger than 1. So we need to take 1 minus P Z lesser than 1 plus P Z lesser than -1 over here. So we just got to key this whole thing into our GC. So 1 minus EISTR here. Upper would be 1, right? Enter. Then now I plus the second one, which is up until -1, and I paste here. So I get 0.31731. 0.31731 dot 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 dot, which is 0.31723 SF. Right? Just a recap. Why this is equals to this. This over here, it means the absolute value of Z being bigger than 1, right? When you have a modular sign, it means absolute value. So if you look at your number line, this is 0, and then, on your number line, this is 0 and this is 1, right? Any other number from here onwards will have a distance from 0 of bigger than 1, right? It will have a distance from 0 that's bigger than 1. And same thing, any number from here onwards, any number over here will have a distance from 0 that is bigger than 1 as well. So when we talk about modulus, we're actually finding out what's the distance of the number from 0. And we see that in both directions, these set of numbers have an absolute distance of more than 1 from 0. So that is how this was actually interpreted in equation and inequalities, the chapter that you learned in J1. Okay, so that's it. That comes to the end of this demonstration question. Now we are going to try and tackle this question for yourself. Okay, so feel free to pause this video right now to tackle it, and when you're ready, come back and let's do this question together. Alright, so let's figure out how to draw this in the first place. We have a standard deviation graph over here. So we know that Z is normally distributed with a mean of 0 and a variance / standard deviation of 1. So if I were to draw this over here, right, let's say here is 0, and we know that from 1, so 1 and A, right, this whole area over here is being represented by P1Z lesser than A equals to 0.1. So now we want to find out what is A, right? So how exactly can we actually tackle this? Well, first thing is that we know that this whole area over here can be represented in another way, right? We can also represent this area here as P Z lesser than A minus P Z lesser than 1, right? Because if we take P Z lesser than A is effectively this whole thing here, then we minus away P Z is lesser than 1, which is this, we end up with this. And this whole value equals to 0.1. So for P Z lesser than A minus P Z lesser than 1 is 0.1. Realize that I can bring this over to the right hand side. And when I do that, I end up with this as 0.1 plus P Z lesser than 1. And this is something that I can key into my calculator, right? So second DISCR lesser than 1. And then I key in, I get 0.84134 dot 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 dot. So here I get 0.1 plus 0.81344 dot 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 dot. Sorry, 43. So 4134 dot 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 dot. So I get 0.941344 dot 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 dot, right? And so far this is to 3, not 3, I mean this is the intermediate value. So now that I know that Pz lesser than A is this, how do I actually find out A? Well, this is where, if you recall, your inverse norm function is something that you can apply to all normal distribution curves. And a standard normal distribution curve is also a normal distribution curve. So from here, you can directly calculate it from your GC, right? And how you do that is, first thing, over here, I'll plus 0.1 first. Not sure whether you all can see it, so I'm just going to scroll down. Okay, I'm going to plus 0.1 first. And then this value is very critical to me, right? So I'm just going to store it under A first. Store under alpha A, enter. So now this value is stored inside A. Then from here, I'm going to inverse norm, area would be 8. And now this is a left tail. Recall, you see this is a left tail, right? It's pointing to the left side. So it's a left tail. These two are the parameters of the standard normal distribution curve, and my area is 8. So you can press paste, enter 1.56616. Over here, I get a value of 1.56616 dot, which is 1.5723SF. And that's the final answer to this question over here. Okay, so I hope that this explanation was clear in terms of what not standard normal distribution is. If you got any other questions, feel free to raise it up in the comments below or through WhatsApp. If not, I'll see you in the next video.